Okay, everyone, let's get started, please. It's my pleasure to introduce this morning's speaker, Dr. Hal Weaver. His middle name should be Comets, because he is one of the world's foremost cometary scientists. In spite of being interested in icy bodies, he's really a nice guy. I've known him for a long, long time. He's a Hopkins Ph.D. and he's been working at Hopkins for the last 13 odd years, both as a research professor on the Homewood campus as well as out at the Applied Physics Laboratory in Laurel. And anytime I mention APL, I have to always mention, APL is an offshoot of DTM. As you probably already know. APL's founding director, Merle II, was DTM's director. The founding of APL was part of DTM's war effort, which Carnegie relinquished after the war was over, and Johns Hopkins said, "We'll take that. Thank you very much." So, in some sense, you are a sibling of DTM through that connection. So, Hal has been very active in studying comets. He's basically the person who really made the case for definitely there being water in comets. And through a variety of mostly space-based observations, using IUE and Hubble and other space telescopes. He's also part of the Rosetta mission, and of course he's the principal scientist for NASA's New Horizons missions, which will be the focus of today's talk. So Hal, take it away and turn on your microphone and let's hear what you have to say.
Okay, thank you very much, Alan. Indeed, I do love comets, and that has been my only regret this year, is that this mission happened to land right on top of the Rosetta mission. I'm on both of them, so actually I had to spend most of my time working on New Horizons, but that's been a lot of fun. Just 4.5 months ago, of course, the New Horizons spacecraft passed just 12,500 kilometers above the surface of Pluto. This is a little artist's view of what the spacecraft looks like during the approach to Pluto and Sharon. But this is what it really looked like. This is an actual image taken by the New Horizons cameras with the true scale here, an iconic view of Pluto and Sharon. You can see from their color, they've been colored with natural color. You can see the dramatic differences between the two. And then we flew by on July the 14th, and this is a view looking back towards the sun, and a spectacular view with incredible haze in Pluto's atmosphere. And I'll talk a lot more about that in a little while. Before I get into the results from the mission, let me first of all give you a little bit of background information, talk about the motivation for the mission, just so that you'll be able to put the other stuff in context. This is the first mission to what we call the solar system's third zone. If you think about the architecture of the solar system, you get the terrestrial planet region and the giant planets. And New Horizons is the first journey into the third zone, the newly discovered Kuiper Belt, discovered in the early 1990s. And of course, there have been other spacecraft that have gone into that zone, but to actually encounter objects that live there. This mission, New Horizons, is the first in NASA's New Frontiers line, which was in fact invented around the time that the New Horizons mission was accepted as a mission by NASA. Back in 2001, late 2001, it became a line item. It's a mid-class mission. This mission, it's run by a single principal investigator. It's not with a team of people. So that person is Alan Stern in this particular case from Southwest Research Institute. The program management is done by Hopkins Applied Physics Laboratory. There's a little cartoon showing the solar system in the Kuiper Belt, illustrated by these little white dots, just sort of a torus-shaped region surrounding the sun. We launched in January of 2006, and just a long way out there, 30 AU from the sun is Pluto, and it takes, despite the fact that New Horizons was the fastest spacecraft ever.
40 AU, isn't it?
Well, it has right now it's about 33 AU from the sun.
Okay, it varies.
Yes. Yeah, and that's one of the unusual aspects of Pluto's orbit, and that's why it stood out so much relative to all the other objects in the solar system. It was first discovered in 1930 by Clyde Tombaugh at the Lowell Observatory, and it has an inclination of about 17 degrees, eccentricity of about 0.25, so it actually comes inside of Neptune's orbit, which it last did in 1989, at about 29 AU, and it goes all the way out to 48. And it's on its way out now. this is the frontier of planetary science, both literally and figuratively. And the discovery of the Kuiper Belt would really motivated the scientific justification for this mission. It's a whole new region of the solar system that, with the discovery of 1992 QB1 by Jewett and Jane Liu, things just took off from there. And the neat thing is, this time frame, early 1990s, also coincided with the discovery of all these exoplanetary systems. That's when that started heating up, and it's just noteworthy that both of those things are happening at the same time. And those two things, the discovery of the Kuiper Belt and the discovery of other planets around other stars, has really, motivated a surge in our interest in the formation and evolution of planetary systems in general. Because we think by studying these systems, including the Kuiper Belt, that that we're going to learn a lot more about the architecture of solar systems and planetary building processes. As I said, here's the orbit of Pluto. It is highly eccentric. This is from Paul Chodas from JPL, shows you actually all of the outer solar system objects currently cataloged as of midsummer, this summer. Okay, the comets are these little caret symbols. The yellow dots are the known Kuiper Belt objects, and they're up to about 1,500 or so now. There's a lot of objects out there. It's probably the most populated region of this region, within 40 AU of the sun, more so than the asteroid belt. They're probably on the order of 100,000 objects larger than 100 kilometers in diameter in the Kuiper Belt. If you look at it from that was the top-down, top view from the above the ecliptic. Now, if you look from the side and you see that inclination that I was talking about earlier for Pluto's orbit, highly inclined, you see the sort of torus-shaped arrangement for the Kuiper Belt objects, and a lot has been done, of course, in the study of the Kuiper Belt over the last 15 years, and in fact, we know that it has quite an intricate and interesting architecture itself. Basically, just in the simplest terms, it divides into three different kinds of objects. You have the classical Kuiper Belt objects, which probably formed near the plane of the ecliptic and in place where they are today, or nearly so. In fact, after we've passed by Pluto, we've identified one object in that cold classical family of objects that we could potentially fly by in an extended mission, and that's what we're going to be trying to do. We already know. Yeah.
What would New Horizons trajectory look like from the side view? Is it up at 17 degrees or something?
No, and this is one reason why this was timely, that we could do this mission now, is because Pluto was flying through the ecliptic plane. This enabled, really, this was a once-in-a-lifetime opportunity. And, so we could fly by Pluto without a huge, it was already taking, a huge amount of energy to get to Pluto. To have to actually go out of the plane would have been even worse. So we happened to be here at the time when we could do this mission. And in fact, the other thing that really helped our mission was the alignment with Jupiter. So that in January 2006, that was the last window that we had that we could launch and still get a gravity assist from Jupiter on the way out. Okay, beginning back to the, yeah.
When Tom Bob found it, was it in the ecliptic or close ecliptic? Because that's presumably where we would have been.
1930, it was, I don't remember exactly how, where it was.
85 years ago, it's a third.
Yeah, it's a third of an orbit. It's 248-year orbit. In fact, that's the other thing, interesting thing, is we've only observed this object for a third of its orbit around the sun. And it turns out that was a huge issue because we didn't know exactly where Pluto was in radial distance from the sun. And if you can imagine, if you're trying to fly by at 12,500 kilometers over this object, you have to know where it is to much better precision than what we knew when we started this mission. It turns out that we went back and looked back at the old plates. We rescanned all of the old plates from Lowell Observatory going back to 1930 and earlier and all the way through 1950s. Josh Grindley from Harvard rescanned the plates, remeasured all of those positions, and with that new astrometry, that really narrowed down the orbit so that we could then enable this flyby, really.
I think there was a Mount Wilson plate too they found from 1910 or 1920.
I don't know, but the systematic, all taken with the same, telescope at Lowell, measuring those plates, that's what did it for us. I mean, of course, we have OpNav as we're coming in, but we really, but that really doesn't improve over what we learned from those plates until the last week or so. So, anyway, but the big thing, I mean, this is, discovery of the Kuiper Belt and discovery of exoplanetary systems has really revolutionized our view of planetary formation processes, and in particular, in the solar system, it's completely, changed our view of how our solar system formed. There's been a recognition that there's been a huge amount of radial migration of the giant planets during those early stages, the first few 100 million years, and in fact, we now think that Neptune and Uranus actually flip positions. So there's, Pluto may have, Jupiter may have come in to within the asteroid belt, 1.5 almost to Mars's orbit, and went back out again. And the various dynamical resonances between Jupiter and Saturn and all the other giant planets really shook up the inner solar system, and ultimately ended up with, pushing these little planetesimals, these little objects that eventually populated the Kuiper Belt into their current locations. And in fact, the so-called Nix model for the formation of the solar system, was basically born in order to be able to explain these dynamical structures which were seen in the Kuiper Belt, as well as try to explain everything else. This is the model of supposedly explains everything. But anyway, whether or not that's true, it really, just in the past 20 years, basically, our view of the solar system's formation and evolution has changed dramatically. And that motivated, that really is what the planetary community back in the decadal survey in 2002 decided was the highest priority for planetary science in the following decade. It was the exploration, the in situ exploration of the Kuiper Belt, and that's why the New Horizons mission, that gave the final push to allow the New Horizons mission to proceed forward after its selection in November of 2001. Okay, so, but as we were talking about, Pluto is way out there. It requires a lot of energy to get there in a reasonable amount of time, so we had to find the largest spacecraft, the largest launch vehicle available in the United States, which is the Atlas V 551. This is a monster. Everything got cut off a little bit here. It's 200 feet from top to bottom. Here's our little spacecraft, which is about 1,000 pounds, and about the size of a grand piano, roughly 7 feet across, sitting on top of this thing, almost like a hood ornament on a car. But we had this Atlas V 551, which had 5 solid rocket boosters strapped around the main engine. We had a Centaur stage, which gave it an extra kick, and then a final kick provided by a Boeing Star 48 third stage. And, that's what it took to get to Pluto. And even with all of that, it takes 9.5 years. In addition, the gravity assist that we got by flying close to Jupiter, we flew about 33 RJ above Jupiter's surface, and increased the speed by about 20% and cut 3 years off the travel time. So, except for that, we would have taken even longer. Okay, so this is, I always have to show this. Oops. If I can get it to start. Let's see. Here we go.
3, 2.
This is the launch.
We have ignition and liftoff of NASA's New Horizons.
January the 19th, 2006.
Voyage to visit the planet Pluto and then beyond.
This is our third attempt, actually. We had bad weather the first day in Florida, bad weather at APL the second day. We couldn't launch then because we had to take over. This was the fastest spacecraft ever to leave the Earth. You know, about 35,000 miles per hour. It left. We were over the Indian Ocean in 45 minutes. We reached the orbit of the moon. We took off at 2 p.m. By 11 p.m., we had already passed the orbit of the moon. It took the Apollo astronauts 3 days to get there, so we did it, you know, just in 9 hours. So this was.
To stop when they got there too, of course.
Yeah. Good point. Good point. We just waved goodbye. But anyway, this is the trajectory. This is a color-coded view showing you year by year in a different color the trajectory. This is the trajectory of the New Horizons spacecraft and the relative positions of all of the major objects in the major planets. We crossed the orbit of Jupiter we crossed Jupiter's orbit in late February of 2007. So 13 months, only 13 months to get to 5 AU. It took the Galileo spacecraft 5 years to get there. And then we flew through this little keyhole in space where we could grab some momentum, steal some momentum from Jupiter, and increase our speed by 20%. That kept the 3.5 years off the travel time. Okay, so Saturn is way over here. We crossed Saturn's orbit, in 2008. We crossed Uranus in 2011. Sorry, we didn't get all the way out to Neptune until the summer of 2014, and then finally got to Pluto 9.5 years later. And one cool fact is that so it takes 9.5 years to get there, and we hit the timing, our desired closest approach time to within 70 seconds. Over 9.5 years, so that's pretty cool. Okay, this is the spacecraft, and as I was saying, it's about the size of a grand piano. The largest single structure is that radio dish, which is 2.1 meters across. These are the 7 instruments. These are low energy, but high capability instruments, advanced instruments, much more so than, of course, as you would expect. Now that you're 20 years past the Voyagers, they're that much more sophisticated. We have, and in fact, let me just go forward to the, just show you the actual instruments themselves. We have an ultraviolet spectrograph, which is mainly studying Pluto's atmosphere. We have an instrument called Ralph, which is actually comprised of 2 instruments, a color imager in the optical called MVIC, and a near-infrared spectral imager called LISA, and that's to really map the composition of all of the objects we fly by in the Pluto system, from about 1 micron out to about 2.5 microns in wavelength. This radio experiment, which uses the dish, but then in the electronics it has electronics that can process the signal, and has a really cool experiment. I'll say more about this later. To probe the lower atmosphere of Pluto. After we fly by Pluto, we actually flew through the shadow, right through the middle of the shadow of Pluto, and monitored the radio signal from the Earth. The DSN, the Deep Space Network, was beaming up 85 kilowatts of power to the spacecraft. We watched the phase change, the bending of the radio waves as they pass through the lower atmosphere of Pluto, and by measuring precisely that number, you can get a measure of the temperature, the thermal structure, and the mean molecular mass of the atmosphere. Okay, we'll say a little bit more about that later. The instrument that I'm, closest to is the long-range reconnaissance imager, which was provided by APL. It's a fairly large telescope for space mission, 20.8 centimeter diameter primary mirror, a 1 arc-second telescope, basically. And that gives us the highest spatial resolution for the Pluto encounter. We have 2 particle instruments, one of which is monitoring the solar wind. We were, trying to look for where the solar wind was going to be stood off by the outflowing atmosphere from Pluto. Pluto is like a big comet in some respects. It's much, much bigger than a comet, but it has an atmosphere which is escaping to space. One of the surprises that we found, in the New Horizons, results so far, we went in thinking that the molecular escape rate was about 10 to the 27 molecules per second of N2 molecular nitrogen escaping from the top of the atmosphere. It turns out to be about 3 orders of magnitude lower. And we'll say a little bit more about that later. And then we had a higher, another instrument, Pepsi, which is provided by APL. This was provided by Southwest Research Institute. It was measuring higher energy particles, pickup ions. That was what we were looking for from that outflow of material, ionized by the solar ultraviolet and being then picked up by these by this instrument. And then there was one innovative thing that hadn't been on any other NASA mission up until that time. A student designed and built instrument called the Venetia Burney Student Dust Counter. Venetia Burney was the person who was responding. The little schoolgirl in England who named Pluto won that contest. Very nice woman, by the way. But anyway, students at the University of Colorado, under the direction of Mihai Horanyi, who was a dust expert at the University of Colorado, put together, these are just a bunch of polyvinyl chloride panels that measure dust impacts. And so that thing is mounted at the bottom of the spacecraft, and in the RAM direction, the direction of motion of the spacecraft, is counting dust particle impacts all the way along our trajectory. And once we got outside of Saturn, this is actually unique data, hadn't ever been accumulated before. And they did a great job. I always thought of University of Colorado as being a party school, but they were the first ones to deliver an instrument to the New Horizons spacecraft.
So Hal or
Yeah.
Alf and Alice and Ralph named after the honeymooners?
Yes, but we're too old. Most people wouldn't understand. Yep, they were named after the honeymooners, just a television sitcom, Jackie Gleason and
The Cramdens.
the Cramdens, right. Okay, so just to remind you about what the Pluto system is, I mean, it's actually been, when the mission was being proposed and hadn't been accepted, it consisted of two bodies, Pluto and Sharon. Sharon was discovered in 1978, so 48 years after the discovery of Pluto, it took until Jim Christie and Bob Harrington, picked out that, oh my gosh, there's something orbiting Pluto. And in fact, this is the only example of a binary planet system in our solar system. I mean, the center of mass is actually outside of Pluto's, outside of Pluto's radius, in between the two, and so there's like a dumbbell-like arrangement. Those two are rotating about their common center of mass. This is, in fact, the geometry at the time of closest approach. The space, so here's Pluto and Sharon, and this is the arrangement of, okay, in addition to Sharon, then in 2005, we discovered Nix and Hydra using the Hubble Space Telescope. Okay, Nix here, Hydra there, but we didn't give up at that point. In 2011 and 2012, we discovered two more objects. Matt Mountain, the director of Space Telescope Sciences, said he's going to stop giving us time, because every time we got up, we'd discover a new object, But anyway, it did stop at those, at that point. This is an example. This is in fact the deepest image of the Pluto system, and it was obtained by the WIF-3 camera through the F350 LP, a very broad visible light filter on Hubble. And here's the picture. You've got a factor of about 150,000 in dynamic range here between the brightest object, Pluto, and the faintest Styx, which you can just barely make out here. Lots of interesting dynamical properties, associated with this system, including the fact that these satellites, Sharon, Styx, Nix, Kerberos, and Hydra, almost perfect integer multiples, of each other in terms of their orbital periods, around the Berry center. 1 to 3 to 4 to 5 to 6, not quite, not exactly, and that's very interesting for people who study the dynamics. We think that the whole system formed from a giant impact, two roughly Pluto-sized objects having a glancing impact, and then forming a debris disk. It's almost like a mini solar system here. A debris disk within which you form Pluto, Sharon, and then in the rest of that disk, all these smaller bodies. Because they are almost all in the same plane, and they're orbiting in these with these peculiar properties. It's inconceivable that they were just captured from the Kuiper Belt into these kinds of orbits, basically. Now, we still don't have we still can't completely explain dynamically how this particular configuration where we are today, but still most of us think that it was a giant impact that occurred that ended up producing this system. Okay, so as far as there's as for most NASA missions, especially the big ones, you typically have scientific committees meeting over at least a decade, trying to, detail, what should be the highest priorities, and what are the measurement objectives of a mission. And that happened in this particular case too. Started in 1989, worked through the 1990s. There were several false starts, several missions to Pluto that were, sprung up and then were banged back down. But ultimately, finally, the New Horizons project was accepted. And just at the highest level, it's very easy to state the most basic objectives, and that is, just to characterize the geology of Pluto and Sharon, the surfaces of both of them, map the surface composition, and to characterize Pluto's atmosphere. And then there's a whole laundry list of very specific measurement objectives, requirements that are associated with those objectives. And plus, after the discovery of all the small satellites, we added those to the mix. Those weren't part of the original AO, of course. Okay, so it was July the 14th, so we just did this in July. But we already have, our first results came out in Science. The former science editor here watching me here. No, we published in Science, the good old American Science. And we got the cover. This is the beautiful view of Pluto after we flew by, looking back, and I'll say more about that later. But this just came out in mid-October, October the 16th. This is our, presenting some of our quick look results, because in July, we basically only sent back about 5% of the data that we took. And in fact, all of the data had to be what we call lossy compressed, JPEG compressed images that had artifacts in them and stuff like that, because we wanted to spend most of our time actually observing the Pluto system and not turning the spacecraft back and sending data back to the Earth. So we had to wait until after we flew by Pluto in order to send the data back. And that's what we did. And in fact, it's going to take us another year from now before we're completely finished. But the data are streaming in now. It started in September, Labor Day weekend, and it's been a steady stream ever since. And it's just been phenomenal. It's been fantastic sitting at my computer and watching the data every weekend. The first weekend, Labor Day weekend, none of us were on vacation that weekend because just the most spectacular stuff was coming in. Okay, now, this is a little bit backwards because I'm just going to say for you right now, before we see some of the images and some of the data, what's been most intriguing to us so far, and what kind of questions are being raised. Well, first of all, most people did not expect Pluto to be so interesting. Truthfully. We had a science conference, in 2013, summer of 2013. Pluto is sitting out in a really cold area of space with no giant planet tidally interacting with it and heating up the interior. He's just sitting out there. The tidal interactions with Sharon are not thought to be very significant in terms of the heating of the interior. So why the heck is there all of this terrain diversity that you'll see in just a few minutes? How could such a small object, about 3/4 the size of the Earth's moon, be producing this kind of stuff? We're seeing glacier flows. We see all of this. We see giant mountains, huge, valleys, wind streaks. How can small planets, small objects do this kind of thing? Okay, what's powering that? The atmosphere, we've discovered some new hydrocarbons in the atmosphere, and we found this haze. We were looking for hazes, but we were surprised at how easy it was to see, and how prevalent it was. Not only was Pluto diverse and interesting, but so was Sharon, and then the small bodies, the small satellites, the small moons. Been a lot of surprises there as well, which I'll get into. We looked very hard for new moons as we were coming in because we were afraid. In fact, all those small moons are debris generators. They're being pummeled throughout the age of the solar system by smaller Kuiper Belt objects, boulders. And when they strike the surfaces of those small satellites don't have enough gravity to hold on to the ejecta, so they go off into the system. And one thing we were afraid of prior to the encounter was that there was going to be a dust ring around Pluto, and with the spacecraft traveling so fast, 14 kilometers per second through the system, we had even a millimeter-sized particle that could destroy the spacecraft. And we put a lot of effort over 2 years into studying that particular issue. By the end of it, we became convinced that we were very safe because we actually flew on a trajectory that took us through a donut hole created by Sharon. Sharon basically cleans out a toroidal region, a donut around, in its orbit, both by gravity and by, actually just sucking them up, with its, with the body itself, or ejects stuff from the system. And that's where we flew the spacecraft through. Okay, so let's first of all talk about the imaging results. But let's start here. This is the best that we had prior to New Horizons. This is taken with the faint object camera on Hubble. Actually, the highest resolution instrument, even higher than the whiff pics that ultimately came in. This is Pluto, and people worked on these images for like 10 years. And if you watch Pluto rotate over 6.4 days, you can see that there are brightness variations that move in and out, that change. This is a bright spot, but if you now watch Pluto 3.2 days later, that won't be there, and there'll be a different brightness distribution across it. So that we thought that Pluto is in fact has a lot of brightness variation over its surface, and actually has color variation over its surface. So we thought it might be interesting for that reason, but compare that to this. So we got this the night before the closest approach. It's the last view of Pluto when it nearly filled the frame, the field of view of our long-range reconnaissance imager. This is in natural color to the using the filters on the IMVIC camera, putting them and using proportions that we think mimic the response of the human eye. This is basically what it would look like. Here's the heart of Pluto. We call this region Tombaugh Regio, Tombaugh region, named after Clyde Tombaugh, the discoverer of Pluto. Okay, just once again, there. I actually, you see that little bright spot here? There it was. I mean, would you have ever known, though?
Are you sure it's the same thing?
Yes.
Okay.
I did this on purpose. Okay? Mark Gouy spent a lot of time taking those pixelated Hubble views and creating maps of the surface, and in fact, it is. And in fact, that's why we target. This is the close approach hemisphere. We chose this based on the Hubble data. Well, what are you looking at? This is a huge ice sheet made of primarily molecular nitrogen ice with a little mixture of methane and carbon monoxide. Just a huge region. Pluto itself, we now know the size exactly, to within a kilometer or so, 1,184 kilometer radius. Okay, so you can tell that this is a pretty big region. Okay, so the pole is about here, but Pluto is really has a weird geometry. The pole is tilted over. It's actually, has an inclination angle of 133 degrees or something like that. So it's actually below the ecliptic and tilted over to the side. So you have to take that into account as well. It turns out that the coldest regions on Pluto are really around here, where you see this big ice. What we think now, okay, so I'm just going to summarize where we are right now in our interpretation of this. We think there's a huge basin right here caused by a giant impact, probably shortly after the formation of the system. Right here.
Tilt?
Pardon me?
Do we know the tilt
The tilt of the,
of the planet? The dwarf planets.
yes, yeah. Uh-huh. But this would actually tend to move towards the pole over time, because it's trying to, the angular momentum is conserved, and so it tries to, if you take out a large chunk of mass here, it eventually moves up towards the pole. But this is speculation at this point. But we've already started getting in stereoscopic views, stereo views of the surface, and now are putting together a digital terrain model. And this is a low point, okay? How thick this stuff is, well, I'll say more about all this later, but there's this really dark band across the equator. This is the equator, basically. And this is called Cthulhu Regio here. And it actually doesn't continue as a single continuous band all the way around. There are just splotches of it, but once again, dark red material. That may have been in the past similar to this, molecular ices, but struck by cosmic rays or solar ultraviolet light or rainout of the tholins that I talked about in the haze of Pluto's atmosphere, break the bonds of those ices and reform more complex hydrocarbons. Tholins is sort of the classic material that seem to be prevalent in the outer parts of the solar system. Tholins was invented by Carl Sagan and Bishop Carey, the person who worked with him at Cornell, in the lab trying to produce materials under conditions that you have during the formation of the solar system, what you might see in the outer solar system, the materials that you might produce. And they produce these materials called tholins, which seem to be like in Titan's atmosphere, for example, and also populating the surfaces of many planetary objects. Okay, so that was this is, by the way, a false color view, of course, not what your eye would see, but it's not a cheat. I mean, it's just, you use different proportions of the different filters in order to bring out compositional differences. And that's what you're seeing here. Oops, sorry. If you now project that onto a cylindrical map, so this is what you get. And this really doesn't do justice to it, of course, but if you go and download this from the internet, which is, we post this at our site, blow it up and then pan around. There's just so much detail. Once again, this is the equator. We only got to a little bit south of the equator. We can only see, of course, the illuminated portion of Pluto, and we get the highest resolution during that time of flyby. And so that meant the other side wasn't seen with nearly the same resolution, and that's been cut out of this particular view. But we get much, much better than what Hubble could do, for example. But still, this is emphasizing the highest resolution data. I'm bringing this up because these are showing, we actually took a series, this is, in particular, this little lime green thing, this little strip right here. That's our highest resolution map. While we were, the INVIC imager is a time delay integration CCD. So you sweep across, it's very narrow and long CCD that you then scan across the system, which you kind of had to have on this mission because we didn't know exactly where Pluto was, and you had to make sure you captured it. And so it would scan along, sort of like HiRISE on the Mars mission, that kind of a camera. Okay, but while it was doing that, our framing camera, LORRI camera, we had snapping images all during the scan. So that was producing little strips right along here. Those are coming down now. During this past week, and I'll show you a couple of the slides from that. A couple of slides from that. That's our highest resolution data, approximately 70 to 80 meters per pixel. Okay, this is we have, in order for us to be able to talk among the team, we have to assign names to the places, and so we have this whole big elaborate naming scheme. But it's all informal at this point. It'll take years before the formal names are assigned by the International Astronomical Union. But we've tried to follow the general guidelines for the naming of surface features on objects in the Pluto system. So we hope that these are going to go through, but that remains to be seen. But in the meantime, these are informal names. And once again, this Tombaugh Regio is this whole region, but the region where the ice sheet is actually called Sputnik Planum. Okay, you'll hear me talking about that. But there's just a whole diverse range of things. Okay, so here's a little view of the encounter hemisphere. Okay, so you got this giant ice sheet. And what I'm going to do is focus in on these things in the boxes. Okay. So I'm going to pick up a chaos region, a glacier. I'll start with a glacier flow, look down at some pitted terrain. This is north, is straight up here. So this is like towards the north of Sputnik Planum. And then this is in the southeast, southwest, and then over here on the northwest, and then way out to the east is some very interesting region. I'm going to focus in on those. Okay, so the first one up at the northern border of Sputnik Planum, we actually, just look at the swirls and the impediments to flow. That we can actually see flow what appears to be like glacier-like flow. And it turns out, I mean, Pluto's like minus 393 degrees Fahrenheit. You know, it's only about 40 Kelvin. So water ice is like a rock. And so, you know, we're not talking about anything like on the Earth with glaciers, you know, regular water ice glaciers, but molecular nitrogen is so volatile that it sort of has the same properties that water does at, you know, our temperatures here on the Earth on Pluto's surface. Okay, you know, it's a solid, but it's fairly porous and viscous and slushy. And so it can move, and we think that's what we're seeing here. Plus you get all these polygonal you know, structures that we think is probably upwelling and downwelling of material, convective flow. If you go down now to the southeast, this is another example of flow. You see, you know, right here, you see stuff that was in the upper uplands and then flowing down into this region and pooling here. This is molecular nitrogen ice and then other stuff jutting up. These are like pits over here. And you have sublimation, condensation and sublimation and then flow of icy material. Now if you go down to the southwest, we get these mountain ranges. And in fact, they're as high as these are called the Norgay Montes over here. They're as high as the Rocky Mountains in the United States. Okay? We think these are giant water ice mountains. That's those molecular nitrogen ice isn't strong enough to maintain a structure that's that big. Okay, we think these are water ice structures that are poking out of the molecular nitrogen ice. Okay, you see a whole bunch of craters as you get over to here. And by the way, there's not a single crater found on Sputnik Planum, that ice sheet. Indicates that a relatively young surface. There's a huge range of ages on the crater retention ages on the surface of Pluto. As you get over here, you see a lot of craters. You know, we've been counting all these up, and these results will be published soon. You see some filled-in craters. You see some that are, you know, all kinds of different crater morphologies here. If you look at this, also in that same region, I mean, these we're calling these fingerprints. They look almost like flow patterns. That we were wondering whether these could be caused by winds on Pluto, but Pluto's surface, even at the surface, is only 10 microbars, so 10 to the minus 5 of the atmosphere pressure here in the room. So how could that be moving things around? There's such a, you know, a weak atmosphere. Well, first of all, it could have happened in the past if there happened to be a thicker atmosphere, but we think it's more likely is that the motions are determined by the what's underneath the terrain. Here's just another example. I mean, this is, these are like little, we think these are little, you know, maybe little sublimation pits, you know, where you see the black, the stuff is evaporated away. And if you get some dark material, you have sun cups, you know, on the Earth's surface formed when you get a little bit of dirt accumulating somewhere and the focusing of sunlight and producing these weird structures, and maybe the same kind of thing is happening on Pluto's surface. Okay, so now you move up to the western portion of Sputnik Planum, and you see this chaotic region, just a jumble of things, which is reminiscent of what we see on Europa, and what has been termed chaos. You get these, you know, it looks like an upwelling and downwelling of giant chunks of ice, but even on a larger scale here. Here's a scale bar, 50 miles. This is like maybe 10 times larger than some of the things you see on Europa. But that's what we think is happening. Is you have giant water, you know, it's like icebergs, except they're, you know, they really are like rocks, being brought up to the surface and then maybe brought back down again in these regions. And there's a little pool right here of, you know, in the middle of all that, where, you know, it was still a remnant of, but it was all probably like that all around originally. I'm not really supposed to be showing this because this is from that little footprint. I thought it was going to be released today. It'll be coming out tomorrow. We have that whole strip. We put, you know, we don't have all the data down. It'll take another couple of weeks to get all the data down from that high resolution strip. But this is now at about 80 meters per pixel. This is, in fact, it's probably more like 80. Just, you know, at a phase angle of about 68 degrees. So you're very good for looking at surface features. Okay, this is one section of it. Where it was, you know, you just see a whole bunch of different kinds of crater structures look at all the little tributaries here and the chasms. And then over here, as you continue further down, this is continuing up over here and then down into Sputnik Planum. Just look at the detail in this. So, I mean, I'm a planetary astronomer. I'm used to looking at pixelated blobs for the most part, but this has been this is real geology. and so, we have, fortunately, on our team, lots of planetary geologists who've been, studying Mars, surface of Mars, and all of the Galilean satellites and so forth and so on. And we're going to need to bring there are things on the surface of Pluto we haven't seen anywhere else, basically. There's some analogs to some of the stuff that we've seen, but there's stuff that's never been seen anywhere, basically, the types of material. Oops, like this. Okay, so this is far off to the east of Sputnik Planum, and you get these aligned, this alignment of material, and what the geologists are calling hummocky, surfaces. It's almost like a bunched up rug, that you're seeing here. But you have some pooled deposits over here. And by the way, you can see that, with the phase angle for these observations, this is our earliest information on this, on the 3 dimensions. The third dimension was by measuring the lengths of shadows. And this is, you see the shadow here, in addition to the stereo imaging. But this is incredible. This is 25 miles, scale bar for you there. And then this is sort of, one of our favorite views after you pass by, and this was what I showed in the very first slide, but now in greater detail. And I saw this was the week after Labor Day when this came in, and I saw this, I had to call my wife, and I said, I feel like I'm there. These are the Norgay Montes and the Hillary Montes over here. You see their shadows. This is Sputnik Planum, but looking at this very oblique angle, the sun is directly into the page, and look at the structure. I mean, you're seeing the atmosphere. This is haze in the atmosphere, and it's structured, and it goes out to 150 kilometers above the surface. Okay, but just panning around on stuff like this is just really cool.
Is that sunlight illuminating the surface, or
Yeah.
Sharon?
No, this is sunlight illuminating the surface. So, it's just illuminating just a little sliver here, and here's the terminator. Okay. Okay, so on to Sharon. That was Pluto. Once again, we have maps of, so this is a false color image, but stretched exactly the same way that we stretched that Pluto image, that we call enhanced color. And look at this. This is a huge chasm, dwarfs the Grand Canyon, several kilometers deep, 1,000 kilometers across. Looks almost like Sharon got busted open at some time. Pole is here, right up here. And the pole is brown, reddish brown. What the heck is that? That's something we did not know from the Hubble observations. And of course, Sharon is half the size of Pluto, so you can imagine that Hubble couldn't really do anything on significant, spatially resolved on Sharon. Well, I mean, it's sort of reminiscent of that dark band on Pluto. Okay, so maybe it was originally, those ices that then get converted into hydrocarbons. But one interesting thing that hypothesis that we're investigating now is possible transport of material from Pluto to Sharon. Okay, there have been models in the past that have described that interaction. I mean, if you think about the Roche lobe associated with each of those objects, you would expect them to share material. And so we're pursuing that now as one possible explanation for, so you had preferentially stuff being, pushed into this region and accumulated, and this is the coldest region on Sharon, so it would have stayed there. And the reason why you don't have those volatile ices on Sharon is that it's not massive enough to keep those things on its surface over the entire age of the solar system, the 4.6 billion years. And Emily Schaller and Mike Brown wrote a nice paper describing, the conditions under which you would, keep these really volatile species on the surfaces of the Kuiper Belt objects versus not. Sharon falls on one side of the line, Pluto falls on the other. Okay. If you now look in a little bit more detail, here's what we call a mountain in a moat down here. You got a couple of kilometer high mountain in a moat. This happens to be called Kuiper Mons. Just incredible. And then there's some regions in Vulcan Planum on Sharon that very much reminiscent of what you see on the moon. The lunar mare volcanic plains are similar to what we see here on Sharon. But one important point is just comparing they're really completely different worlds. Even though they're formed in the same system, this is, they're stretched exactly the same way, and you can see that Sharon is much more muted, much less bright, about 2.5 times fainter, in albedo than Pluto, and it doesn't have nearly as much diversity over its surface. And I'll show you more about the color diversity in a second. Okay, now let's move on. Yeah.
What's the resolution on Sharon?
About yeah, it's a little bit worse on Sharon. Those are about 0.4 kilometers per pixel, as opposed to 0.3 or something like that for Pluto. Not too far, not too vastly different, but we did get better stuff on Sharon. Oops, the small satellites. So just the whole family at once, including, you can just see relative to Sharon, all of these objects are very small. You get 2 pairs, roughly the same size, Hydra and Nix, and Styx and Kerberos. These are those little pinpoints of light, as observed from Hubble. We knew how bright they were. They were about 20. Styx was about 27th magnitude as viewed from the Earth, but we had no idea what the reflectivities of their surfaces were, nor how, so we couldn't tell how big they were to within a factor of about 5. But now we have resolved measurements, and that's what you're seeing here. And several surprises. One, we have during the approach, we made lots of observations, systematic observations, and we got nice light curves for these objects and found these periods, okay? Styx, 3.24 days, Nix, 1.83, Kerberos, 5.3, Hydra, 10-hour period. If they were synchronously rotating, which you might think would have happened over the age of the solar system, those would be 20 days to 35 days, right? Those are the orbital periods of those objects. They're nowhere near that. Mark Showalter put together this cute little animation. So there they are, sort of, you see, look at Hydra. Spinning like a top, okay? And, that was not predicted, not anticipated. But the brightness of these objects, they're incredibly bright. Geometric albedos of at least, 50 to 60%, probably covered by water ice, just like Sharon is, but even brighter than Sharon, significantly brighter than Sharon, even though we don't have the compositional data down yet. And we won't get that until early 2016, just by virtue of where they, oops, I didn't realize that one was there. Precession of the, let's go on.
So 3 of them are rotating prograde and 1 retrograde?
Right, that's what it looks like. Yep. Okay, so here's color information. So first of all, this is the point that I was just now making about, here's the little woodpecker for Pluto. This is the colors of Pluto, okay, this is a blue to red to near IR a color plot. And these are the wavelengths, which are cut off over here to the right. But just an amazing diversity of colors. This is very red over here to very blue up here. Okay, that's the way the colors go. The sun would be sitting right here at 1,1 on this plot. Okay, Sharon is completely different, but its surface material follows this mixing line right here, distinct from Pluto. Not quite as much diversity, but a fair amount of diversity. And then Hydra and Nix in between the two. Okay, a little bit on the blue side for Hydra especially. By the way, if you look back, you can see impact craters, almost certainly. The spots on Nix and Hydra, we're identifying with impact craters, and in fact, the largest one on Nix is a different color than the rest of the surface, indicating that either you've excavated below the surface and brought up material that's a different composition than what's on most of the surface, or the impactor itself is a different composition, and that's another possibility. But, we actually get cratering ages for both of the surfaces of these objects, and that'll be coming out soon. If you look at Kerberos, I mean, all of these objects are very highly asymmetrical in shape, very elongated, which is sort of typical for small objects in the solar system, right? If you think about how they accumulate, how they formed by merger of smaller objects, and they have so little gravity that they don't have enough to pull themselves into a nice round object, so they end up with however they came together. And in this particular case, it looks like two lobes, two objects that came together for Kerberos. Hydra also has a very weird shape, and in that particular case, I don't think it's quite as clear that there's the merger of a couple of bodies. It looks like it got some stuff whacked off of it by impacting meteoroids, Kuiper Belt, small Kuiper Belt objects. And in fact, maybe that's why it got spun up so fast as well. Okay, geez. I'm having a whole other talk worth going into here, but let me just say, since we're getting near the end, I've got to skip through this, but we do have, this is a data hog. We got three-dimensional cubes, image cubes, produced by the LISA instrument, and it takes up a lot, there are a lot of bits that we have to get to the ground. We're limited to sending data back at 2 kilobits, not bytes, 2 kilobits per second. Okay, so we're going to be sending down data for the next year. Until October of next year, and it's particularly tough on the data-intensive instruments like LISA. But this is a view of taking the LISA data and color coding it according to the composition, because we can see, in fact, let me see if I have it on the next one. Yeah, you can see it has very deep bands of methane. Methane has many spectral bands in the near-infrared spectral region, and so we've mapped the methane. Now, at the time of put this together, we only had data down half of Pluto. So the methane is not in that dark band here, and that's probably because that methane got converted into higher hydrocarbons, I think. But you do see it in Sputnik Planum, and then also throughout. People have been looking for decades for water ice on Pluto, because you figure it must be there. Just cosmogonically, it must be there. And I think that, in fact, it is the bedrock of Pluto's surface, just like it is on Sharon. But the problem is there's just so much methane over the surface, and the absorption is so strong from the methane it masks absorption from the water ice bands. Unless you have spatial resolution, that they can pick out the places where the methane has been scraped off for whatever reason, either sublimated away or something has come up that didn't have methane. And we found some spots that were water ice rich, and these are the spectra. In fact, I think I show it in a little bit more detail here. These are the regions where we see exposed water ice, spectrally. Okay. On Sharon, we've actually found in one crater some ammonia-rich material. Could be ammonium hydrate, which some people have claimed to detect from the ground, actually, on Pluto. But once again, why is this crater different than this one, for example? That's a mystery, and that's the little spectral signature. Just quickly, this is that experiment that I was talking about, where we fly through the shadows. So the trajectory of the spacecraft is this red line, and this is that, the bullseye pattern for Pluto. The sun is off to the right, down here, but these are the orbits of the satellites, Nix and Hydra here, but the whole system is turned over. So you're flying, through a bullseye pattern, but at about 40 degrees to the normal, to the bullseye pattern plane, and we flew, and we hit it right on the button, right through the center of Pluto's shadow. And that allowed us to get, with the Alice instrument, an occultation light curve that looks like this. Okay? It's highly symmetrical, comparing the two sides, ingress and egress. It shows Pluto, and it just shows you where we're going through. And by looking very carefully at exactly the curvature of the curve here, we can figure out what's doing the absorbing in the atmosphere. This is what you see when you have an atmosphere. This is what you see when you don't. So we flew through Sharon's atmosphere, but it wasn't diametric. It wasn't through the center, because we couldn't simultaneously fly through the center of both of them. But you can see how much sharper the decrease is as you hit the solid body, and there's no evidence for atmosphere there. But from these data, we get a very sensitive measurement of the upper limit on Sharon's atmosphere. and that's going to be at the, at least nanobar level, if not even further below that. Just to leave you, this is what was another big surprise. As we flew by, Pluto has a blue sky. Just like the Earth. It has molecular nitrogen. It's dominated. This atmosphere is mostly molecular nitrogen, just as ours is here. But these haze particles in the atmosphere apparently have scattering properties at high phase angles, low scattering angles, such that they look blue. This is a true color. I mean, this is the, using our red, blue, and green and near-infrared filters, what the color of that haze is. If the haze wasn't there, you would just see a little sliver over here. This is a very high phase angle observation, just a little sliver of Pluto's limb illuminated by the sun, okay? But you actually see stuff all the way around. And that's because you have the haze. Okay, so to finish, we hope this mission is not finished, actually. Okay, so we're actually already about 1.1 AU past Pluto, heading deeper into the Kuiper Belt, but the Kuiper Belt is actually peaked up in density at about 43 AU. And we have located a body using Hubble. By the way, we've had a long and successful synergism with Hubble over the years. I mean, not only did Hubble responsible for finding all the small satellites of Pluto, but last summer, something rather miraculous occurred. We had spent several years using the best ground-based facilities searching for a potential Kuiper Belt object that we could fly by in the cold classical Kuiper Belt object, a different kind of family than the Plutinos, which are resonant Kuiper Belt objects. So we wanted to find something in this other class that we could fly by. But you're looking in Sagittarius at something that has to be like on the order of 27th magnitude. And it turned out, that's first of all incredibly hard to do intrinsically, but also it turns out when you look at the distribution, the size distribution of objects, as you get to the smallest objects, it's actually turning over a little bit faster than what we originally thought, maybe by about a factor of 2. Okay, falling off at the smallest size bodies, so it made it that much harder to find. So we hadn't found anything we found like 50 Kuiper Belt objects over that time, but none of them could be reached by our spacecraft. We had to find an object that would be at the right place at the right time. We only had enough fuel on board to divert the trajectory by plus or minus 1 degree in angle. Okay, so that defines a little cone in space. And none of the objects that were found by the ground-based search were successful in turning up something that we could fly by. So we went back to Hubble, and we got 194 orbits of Hubble time last summer. This is an unprecedented program. It went through the TAC. I have a lot of respect for this is, astrophysicists who realized that this was an important once-in-a-lifetime opportunity to be able to fly by a cold classical Kuiper Belt object. It's worth investing a huge amount of Hubble time to search for such an object. But, now we're talking about mid-June when the TAC met, but we had to start these observations the following week if we were going to carry it out, because opposition was around the first week of July, and we had to get some pre-opposition observations. And the TAC approved and the director approved on a Friday. We observed on Monday. Because we built 2 SMSs, Science Mission Specifications for Hubble, the first time they've done this. Depending on what the TAC said, they would do either one or the other. So fortunately, we won. And not only that, but we found a handful of objects, cold classical objects, including this one, PT1, 2014 MU69, that we can reach easily. And in fact, we just made the burns on the spacecraft 2 weeks ago to set us on a trajectory to put us next to PT1, and the time of closest approach we already know, January the 1st, 2019. So New Year's Day, 2019, but we still have to get past the hurdle of a senior review. We have to submit a proposal to NASA. NASA did approve firing the hydrazine thrusters to put us on the path to enable the mission, but we still have to demonstrate that enough good science is going to come out that they can approve the operations that are necessary to have us actually execute in January of 2019. So that's where we're headed. Like I say, there's stuff coming in all the time if you want to keep up to date. go to our website or NASA's website. They've been really good at every week we've been putting out image releases showing you what new stuff has come in. So it's been a wonderful, thrilling ride, and I hope you've enjoyed this. Thank you.
Okay, let's have some questions. We should thank Hal for showing us something that human beings have never seen before. It's a once in a lifetime, once in a species type moment. So, Larry?
So, I mean, I don't care what the IOU says, Pluto's the best planet.
All right.
I do want to ask,
Yeah.
You mentioned early on that the ice in Sputnik region is molecular hydrogen, or nitrogen.
Right.
But then you showed this methane map and
Yes.
made it look like it's pure methane. So
Yeah.
what, I mean...
Oh yeah, no. Okay, since it's a homonuclear molecule, molecular nitrogen has only very, very weak absorption features. Okay, methane has these incredibly strong things, so that makes it easier to see. So we can tell everywhere. But it turns out,
Can you estimate the amount?
yes, we can. For both methane and because we have lots of bands, and for molecular nitrogen as well. And we see molecular nitrogen basically all over the place too, including in Cthulhu region as well. So, and you know that if you see it at all, if that spectral line is there at all, it's a huge amount of it.
Right.
So yeah, I mean, it is dominated by, in terms of the column abundance of stuff, it's molecular nitrogen. Yeah.
Where do you get the power for all the data transmission?
Yeah, we have, our transmitters are like 25 watts each. We have 2 of them. And X-band, transmitters. And,
All sun?
pardon me?
All from the sun?
Power source.
No, I'm sorry. Oh God, I'm sorry. I thought you were talking about our radio communication transmitter. No, the power. I didn't even mention this. The power source is RTG, radioisotope thermoelectric generator. It was a spare from Cassini, and so we started out at about 250 watts of power. Even though Cassini was well preceded, our mission, and has a lifetime half-life about 80 years or so, 76 or something like that for the plutonium-238. Plutonium-238, and it's physically hot, stuff, and we use those to power thermocouples. Yeah. Okay. Yeah.
Dick.
Hal, I assume these mountains and the chasms, Pluto and Sharon, suggest some lingering internal heat source. So what are your geophysicists, Bill Buchanan or Francis
Right.
Lowe,
Well,
wondering?
I didn't bring him up by name, but at that conference, the 2013 conference, it was Francis Nimmo, who I was really referring to, who said this is going to be boring. It couldn't be boring because there was no energy source that could power the kind of terrain diversity that we're seeing. Maybe the heat transfer that we were, assuming had taken place, from the radioisotopes, internal radioisotopes, is not as efficient as what previous thought. So, and there is also the question: how old are all of these features? And there's a variety of ages. I mean, the Sputnik Planum is there's no craters, so it's probably on the order of 100 million years or something like that. But some of the other stuff is 4 billion years old. So, so that's still early enough that maybe you could have generated some stuff, some of these terrain features. But there's stuff going on now, and there's the motion is what we were talking about earlier about the relatively mobile molecular nitrogen ice. That's clearly moving around, and it's also so highly volatile that you can have condensation and sublimation cycles occurring that redistribute stuff over the surface. But the ultimate heat source we don't know. Yeah. In the papers that will be coming out soon, we still don't have an explanation for exactly what we're seeing.
Tommy.
Can I just quickly follow up on that? Why couldn't the heat source be a relatively recent giant impact, not something happening 4 billion years ago, say a billion years ago?
You're right. I asked the same question. I was wondering, well, except that, just the frequency of impacts and what we think the Kuiper Belt population, the density in the Kuiper Belt. I mean, it was much higher. It was probably 100, up to 10, or maybe even 100 Earth masses of material out there, at the 4.6 billion years. But then it quickly, went down dramatically. And so, a recent impact for an object that size would just be highly unlikely. That's the main reason why. And we don't see, you know, when I asked about, you know, in fact, I was wondering if the basin where we have Sputnik Planum, could that be a remnant of the giant impact that produced the two objects in the first place? Bill McKinnon says no. You know, I don't really know, you know exactly why, but it's once again.
Alicia?
Yeah.
In your looking back photo, it seemed that there were striations
Yeah.
in the atmosphere.
Yep.
Is that an artifact?
No.
Or what's the reason for the striations?
We don't know, but it's real. I mean, we're convinced that we see it with two different cameras, and you know, it's you know, almost like cloud formation at different heights for different reasons, and people are working intensively on that now.
Are you avoiding the term haze layers?
No. I think there are haze layers.
Alicia?
So in the region where you have the tholin or supposedly
Yeah,
tholin condensates, do they not have any 1.6 micron features that would nail what their composition is better than?
Those things are, it's almost like, I mean, they're almost featureless in that region. I mean, we've done the modeling for the optical constants of tholins, and then you mix it together with the methane, and you don't really see any strong spectral signature in any of those models that we've seen so far. I mean, it's mostly from the visible light stuff where you see it's just really red and dark.
Okay, John Chambers?
Do you see much CO and CO2 as well as methane?
Yeah, no, CO is there. You see the CO, and it's sort of just like the, it's a little bit less abundant in the, it's, all three of those species, molecular nitrogen, methane, and CO, are also in the atmosphere as well as on the surface. We see the solids on the surface and the stuff in the atmosphere. And it's dominated in the atmosphere just because of the higher volatility of N2. But we do think this, you know, the surface is dominated by the N2 as well. But yeah, no, we see the CO, we see the spectral absorption of the CO. And it is in Sputnik Planum, and there's some other places over the surface as well. It's relatively weak. It's a complicated instrument. It's very hard to pull out stuff, but it's, you know, it's there. CO2, no.
Nikki and then Brad.
Regarding the red spot on Sharon,
Uh-huh.
did you impact?
Yeah, so that was one of the first things that, you know, we thought it might be a depressed region. It could be an impact, and maybe we've dredged something up. And but there's, you know, so our cratering experts have looked to see whether they see any evidence at the anti-spot, if there's any feature that could be associated with the, you know, that you would see if you saw an impact here. You see on the other side. We don't see any evidence for that. And you know, it's actually it doesn't look like an impact crater either. So, yeah.
Brad?
For the N2 isoplanes on Pluto, I mean, do you think it's definitely solid ice, or could there be liquid subsurface?
Yeah, definitely. We think there probably is some liquid underneath the surface, and maybe that's, you know, enables some of the upwelling and downwelling is being caused by that. There's a temperature variation as you go from the surface down below. Yeah, so all that's happening, and that's being modeled as we speak, you know, basically that kind of stuff. But how thick is that layer, you know, which is related to, you know, the formation of those polygonal structures, you know, because we think that's convection taking place driven by temperature gradients. You know, what do you need in order to, and a very large size of those polygonal structures must mean, it seems to mean that the ice is pretty deep. I mean, but is it 4 kilometers or is it 30 kilometers? You know, where did it all come from in the first place? You know, and you know, anyway, we're working on all those issues.
Okay, Aki and then Nancy.
So the dark splotch
Yeah.
on Sharon, you said it's at the pole?
Yeah.
And you had said, I thought, that perhaps it was transfer material from Pluto. How would that end up on the pole in the absence of, like, magnetic field directing it down on the pole or something?
Yeah, I don't think that the material, yeah, so the whole, you know, hemisphere, Pluto-facing hemisphere would be dusted with this stuff, but you would have a natural cold sink at the pole. Okay, so it's colder than the rest, and so maybe you had a concentration for that reason. You know, it's driven by being colder there. And in the case of Sharon, unlike Pluto, that is the coldest region
Yeah,
the
but
surface.
wouldn't material have to vaporize first? to
Yeah,
condense
well,
onto
you know,
the pole?
and you know, if you remember, you know, with the gravity of Sharon being so much less than Pluto's, and these being highly volatile species, they do escape. And that's why we don't see them on most Kuiper Belt objects that are, you know, even very, very large. All the dwarf planets, none of them, only a handful of them have, you know, these ices. So in the case of, so if you had a cold trap at the northern pole, plus the irradiation, cosmic rays and ultraviolet light, that then, you know, now breaks down that ice and converts it into something less volatile and now sticks around and becomes red and dark.
Okay, so actually maybe it's more that the other parts have been cleaned.
Yeah. No,
Actually,
that's another way of looking at it.
deposit
Yeah.
on the pole.
Yes.
Okay, got it.
Oh
That
yeah.
makes
Sorry.
more sense.
That's the real explanation.
Yeah, okay, got it.
Nancy, please.
I have two simple questions. One is, on your first slide, early slide, you said that this was the most easy, most accessible of the Kuiper Belt object. What made it the most accessible?
Well, you know, it is on the inner edge, you know, of the Kuiper Belt. You know, roughly 30 AU. It's also, I mean, we've known about it for a long time, so we, you know its orbit, you know, better than most, and in fact, it is, you know, passing through the ecliptic plane around now, which enabled us to do the mission. I mean, that's the other thing.
Well,
The
it's a
other
planet
question
when it
is
left,
how
also.
much
And it was also a planet.
ability to change the direction of the spacecraft
Right.
that you have near the planet.
Yeah. So we have just little hydrazine thrusters, like 4 newtons, and you know, so not much, but it's limited maneuverability, but it's enough to move us. Like for example, now, like I was saying, plus or minus a degree, you know, can change our trajectory to, you know, to enable us to go to another Kuiper Belt object. But you know, it is limited. So we're traveling at 14 kilometers per second. With the hydrazine that we have on board now, we have left enough for about 150 meters per second. So that's the magnitude of the change in the velocity that you can make with all of the hydrazine that's on board now.
Okay, one last question, I think, Steve.
To come back to the dark spot at the
Yeah.
North Pole of Sharon. What about the South Pole? Is there anything dark there?
Maybe. We can't see it. We can't see it.
I thought you had checked for some.
That was checking in a spot. Yeah. Let's see. So, where was that?
You certainly require a dark spot there. If the cold
You would
is
think.
correct.
Although I tell you that the seasons on Pluto are really weird because of its, you know, the way it's tilted, and you know, and it's a highly elliptical orbit around the sun. Rick Binzel, you know, has been working with his grad student heavily on that. Not sure about that, Steve. I don't remember.
Okay, if there are any more questions, come down and ask Hal about them after the talk, but for now, let's thank him once again.